In this video, we're going to talk about inflection points. So naturally you're thinking, what is an inflection point? So suppose you have a function f that's continuous at the x value x equals a. So if f changes concavity at x equals a, then we say the point a comma f of a is an inflection point of f. Alright, so in other words, it's a point on the graph where the function changes concavity. And so if it's changing on concavity, that means it's changing from concave up to concave down, or from concave down to concave up. Okay, so let's get a visual representation of what an inflection point is, because I feel like that just helps me understand the definitions better. So here, let's just look at this visual, and I have this curve drawn of this graph of this function, and here you can see that it's highlighted that this point here, a comma f of a, is an inflection point. So here it's talking about this point on this graph being an inflection point. And so we can see that what's happening here to the left of this inflection point, you see that the graph is concave up since it's bended upward everywhere that I just highlighted in orange. And then we see to the right of my point here, my inflection point, that the graph is concave down since it's bended downward. And so you can see a little bit better, a little bit clearer, that this point is in fact an inflection point, because you can see that at that point the graph is changing from concave up to concave down. In other words, it's changing concavity. Okay. And so here you might be thinking, okay, well, what does this have to do with calculus? Like, couldn't we have established graphically what an inflection point is based off of more of like pre-calculus knowledge? And you're absolutely right. But why we're studying inflection points, particularly in calculus, is because we want to know how to find inflection points of a function algebraically. Like, say we weren't given the graph, and in fact it'd be hard for us to understand graphically speaking. How would we actually do this if we had a physical formula for the function itself? So no graphs, just algebraically, how would we figure this out? So here I'm asking you guys to just recall the statements that we were talking about earlier in this unit. Okay, in particular, the one that related the second derivative to the first derivative. And so we said here that if a function f, if its second derivative is positive on an interval, then that means the function f is concave up. And then we said if the second derivative is negative on an interval, then that means the function is concave down on that interval. Okay, and so what we're going to do is actually use those two statements, okay, because remember, an inflection point is a point on the graph where we change concavity. Okay, so we're going to use the fact that we know things about concavity of our original function f based off of our second derivative. So here I'm saying that we know that for a point x equals a, where when I plug in that point to the second derivative, I get 0, or when I plug in that point to the second derivative, I get that it's undefined, we're going to say that it's a candidate for an inflection point. Okay, so this doesn't necessarily mean that that point is in fact an inflection point necessarily. All right, and so what we're going to do to determine whether or not this candidate for an inflection point is actually an inflection point or not, we need to check if the second derivative changes sign at x equals a. Okay, because if it changes from positive to negative, or negative to positive, then we know that the original graph of the function is switching from concave up to concave down, or from concave down to concave up. All right, just from the fact of these two statements. Okay, because clearly if we have that the derivative is changing from positive to negative, we would see that the graph is changing from concave up to concave down, right? And then vice versa, if we were going from negative to positive, we would be going from concave down to concave up. All right, but in either case, we're definitely switching concavity. All right, and so that's where this note comes in. I'm saying note the following. if the second derivative changes sign at x equals a, then x equals a is the location for an inflection point. However, if the second derivative does not change sign at x equals a, then x equals a is not the location of an inflection point. All right, so that's what we're going to be doing. We're going to be trying to find the candidates for inflection points, and then we're going to determine whether or not the second derivative changes sign at that candidate for an inflection point. If it does, then that means it's in fact the location for an inflection point. If it doesn't, that means it's not an inflection point. All right, so in the next video, you'll see me do out an example algebraically, but I hope that this video helps you understand the concepts.